Hello, my name is Andre Richter. Welcome to my presentation introducing a new workflow for the fabrication tolerance-aware schematic-driven PIC design. State-of-the-art in PIC design makes use of foundry-specific model libraries of process design kit building blocks. They are used to build parameterizable circuit structures which can be simulated and optimized, such as this example design of a Mach-Zehnder interferometer. The structure is put into a virtual testbed to simulate its optical characteristics and to export the circuit layer to any supported layout tool format. Fabrication tolerances can be accounted for by setting random values to user-controlled parameters and performing statistical simulations. A typical problem with this approach is to obtain information about these random parameter dependencies. Furthermore, how can the chip behavior be predicted if not all influencing parameters and their values are known? So, taking a simple waveguide, we have only two user-controlled parameters, the length and width of the waveguide. Taking an MMI, there is typically no user-controllable parameter. Its characteristic is described directly by a confidential S-matrix. However, a lot of internal parameters affect the overall performance of the chip and therefore need to be taken into account for the tolerance analysis. Moreover, some of these parameters are directly related to the module, while others might refer to the wafer they are produced on. Any of such parameters cannot be utilized by the user directly. This would disclose the foundry intellectual property and furthermore make circuit simulations overcomplicated. Let's take a deeper look on how such tolerance-aware compact simulation modules are created. Taking the waveguide example, we can describe its characteristics by the transfer function shown here, assuming that back reflections and mode couplings are negligible. To calculate effective mode index and mode attenuation, we need to analyze the modes propagating in the cross-sections. For this, we need additional information such as the heights of all layers and refractive indexes. Now, accounting for fabrication tolerances in the simulation, we need to consider all the variations of both user-defined and hidden parameters, as well as the distributions provided by the foundry. This is quite complicated. So we realize a single switch parameter that controls the consideration of fabrication tolerances. This allows to keep the complexity inside the CSM at reasonable level and protect the intellectual property of the foundry. A similar approach can be taken when simulating the characteristics of an MMI device. Its S-matrix depends on many hidden parameters. It shows a varying frequency dependency due to tolerance variations. Again, the fabrication tolerance parameter is used to switch on/off the influence of variations of any hidden device parameter. And if you want to distinguish building block level and wafer level tolerances, you can add more simulation parameters and account for their potential correlations. So let's apply this approach to a simple unbalanced Mach-Zehnder interferometer, as depicted on the left-hand side here. On the right, we see the spectrum with three spectral range and resonance frequencies for the case that the nominal width of the waveguide and MMI are met. Now, considering fabrication tolerances and running the simulations for 1000 iterations, we see strong fluctuations of the resulting transfer characteristic. While the free spectral range stays rather constant within 0.1 GHz here, the resonance frequency shifts dramatically due to the phase noise introduced by the randomly varying device parameters. The standard solution to this problem is to add a thermal or electro-optical phase shifter in at least one of the arms of the Mach-Zehnder interferometer. By applying the control current or voltage to the phase shifter, we can tune the phase in the arm of the MZI, and with this, the resonance frequency of the frequency response. To support this operation, we realize a second switch parameter in our models, compensate phase noise. It enables an automated phase noise compensation at a certain reference frequency and consequently emulates the impact of an optimized thermal or electro-optical phase shifter. All other effects of fabrication tolerances on the device performance are still considered with this. Now, playing the automated phase noise compensation, here for a reference frequency of 193.1 THz, we see a drastic improvement of the overall MZI performance. Note that we can still see some fluctuations of the resonance frequency of the device. This is due to the fact that tolerances in the MMIs and of the waveguide attenuation are not compensated for yet. Further, we can track and display as histogram the total phase shifts applied to the upper arm of the MZI. Considering a power efficiency of the tunable phase shifter of 5 degrees per milliwatt, the power distribution on the right-hand side can be derived. Now, let's come to a more complex example design based on an optical neural network structure. An ONN consists of several layers that are connected with each other, forming a programmable structure with M inputs and N outputs. Each of such ONN layers consists of an optical interference unit and an optical nonlinearity unit. The internal parameters of the ONN are typically obtained by using an iterative algorithm that tries to match a known set of input and output values. Electro-optical implementations of such signal processing units are of interest for the community for an energy and size-efficient realization. Here we show the test structure for such an ONN, a programmable logical gate which can perform different logical operations depending on how it's trained. The logical inputs are encoded via input powers, logical 1s by 10 milliwatts and logical 0s by 0 milliwatt. The third input serves as artificial bias as suggested in reference 2 below. Our ONN consists here of 2 hidden layers. Each layer is made up of a 3x3 optical interference unit and a 3x3 optical activation unit. It is trained by Neuroptica by using a chip-based backpropagation algorithm. The ONU consists of 3 all-optical sigmoid activation units, which are based on the SOA MZI structure shown here and referenced below. For an efficient simulation, we want to use a behavioral model that is characterized by the nonlinear transfer function of the activation unit only. So we place a PIC structure into a virtual testbed and find the transfer function of the activation unit. The result shown here is created for when all the deployed MMIs show the nominal device characteristic. And here we see the transfer function of the AU, how it would fluctuate when MMI tolerances occur. Clearly, an automated power adjustment has to be introduced before each OIU to compensate for these random power variations. So taking a derived transfer function of the activation unit, we fit it with the analytical sigmoid function and extract the corresponding fitting parameters. This allows us to drive the behavioral model of the activation units inside each ONU. Now, looking at the internal structure of each optical interference unit, we see that it is built up of MZI meshes. In total, there are 9 phase shifters, 3 at the inputs and 2 in each of the 3 Mach-Zehnder interferometers. These phase shifters are adjusted during the training of the ONN to make it perform a specific logical operation. So for any 2 input powers, a certain output power should be delivered. Also, we see here the progress of convergence for such a training process. After 2000 iterations, optimized values for all the 9 phase shifters per OIU are obtained. So here are some results for the ONN in action for 3 different target logical operations. Starting from the left, we have XOR, then OR, then NOR operation. For all 3 conditions, we see that the simulation results are identical with the expected outcomes of the device. Now, taking fabrication tolerances in the OIUs into account, the outcomes start to deviate from the expected ones. We see it here for the case of XOR operation. Note that the automated phase noise compensation was enabled. The variation of the output powers is due to fluctuations in waveguide attenuation and MMI width, changing the OIU transfer characteristic. The applied amounts of phase compensation in all the 18 phase shifters can be tracked, and its histogram is displayed here. This gives further insights in the requirements for operating and controlling such a device under the influence of fabrication tolerances. In summary, we presented a general purpose design framework that provides easy access to statistical performance techniques and a convenient way for modeling fabrication tolerances inside PDK building blocks. Our proposed framework allows to identify critical light paths in a given circuit design and to automatically compensate for the phase noise introduced by fabrication tolerances. I showed the operation of our methodology using a simple unbalanced Mach-Zehnder interferometer structure and a more complex programmable logical gate PIC design. Thank you very much for your attention. Please contact us if you want to learn more about our solutions.